There are many different ideas about how to get payloads into space without using rockets. This video is about the ideas that are gun-like. It's guns to space. After I finished this video, I found some rare footage of a government trip to the moon. And after that bit of fun from 1902, we can move on to the main topic. Let's say we want to send cargo to the International Space Station. We first need to get to 400 kilometers. Then we need to go sideways fast enough to stay in orbit, which at 400 kilometers is 7,672 meters per second. The majority of the energy used to get into orbit goes to getting up to orbital speed, roughly 90% for this orbit. We generally talk about this in terms of delta V, which is how much acceleration potential we need. It's about 9,000 meters per second total. We also need to make sure we don't hit the Earth. If we launch on a ballistic trajectory from the Earth, that trajectory will run back into the surface of the Earth. We will fix that by doing a circularization burn, typically done at the high point, or apogee of the trajectory. We'll start by looking at conventional guns. Why can't we just build a big gun? Well, there's some problems with that approach. Here are some numbers from a 155 millimeter, or about 6-inch, artillery gun. When the gun fires, the projectile is obviously just sitting there. The propellant converts itself to gas and creates a lot of pressure inside the gun, and that accelerates the projectile very quickly, at up to 100,000 meters per second squared. But perhaps 1/100th of a second later, the projectile has moved 3 meters and is traveling at about 600 meters per second. The gas has expanded a lot, and therefore the pressure has dropped way down. That means the force accelerating the projectile is much lower. Step forward again, and the projectile has reached the end of the gun, traveling at 820 meters per second. Can we build a better gun? We can use a longer barrel, which gives more time to accelerate the projectile. Or we can use more propellant. Naval guns in World War II were tunable based on how much propellant was used. This picture shows the projectile and powder bags from a 16-inch naval gun, which fired a projectile that weighed about 1,000 kilograms. But that still only gets about 850 meters per second. In the 1960s, there was a project known as HARP, for High Altitude Research Project. The goal was to see if it was possible or practical to use guns for orbital launch. HARP started with a 5-inch gun, shown on the right here, and moved on to 7-inch guns. Both guns had significantly extended barrels to produce the maximum velocity. This approach requires supporting cables on the outside of the barrels to keep them from bending too much. After initial tests with these guns, HARP upsized. The U.S. Army obtained surplus battleship gun barrels from the Navy for the project. They were 16-inch or 406mm barrels, which HARP bored out to 16.3 inches or 414mm to convert them to smooth bores. Then, following their usual approach, they stacked 2 barrels end to end and added a supporting structure, ending up with a gun with a 116-foot or 35-meter barrel. One of the problems with firing projectiles for altitude is that a big 16-inch shell has a lot of drag and therefore slows down quickly. This problem has already been solved. A thin and very dense projectile is wrapped in a shell that detaches early in flight, leaving a low-drag projectile traveling very fast. The popular name for this comes from the French word for hoof or shoe, which is pronounced sabot if you are French or British, sabot if you are American. Here's a picture of the sabot falling off a projectile after it has been fired. The designs for HARP were quite simple. There was a metal pusher disc at the back and a plywood sabot around the projectile. I was very disappointed that I could not find video of HARP in action, so we will have to settle for this color picture. This firing is from the main HARP site located on the island of Barbados in the East Caribbean, which was chosen as it was close to the equator. The 16-inch HARP ultimately achieved an altitude of 180 kilometers with a 436 kilogram projectile, which is in space, but is unfortunately missing the going sideways very fast part that we are looking for. There were projectile designs for the 16-inch gun to launch a rocket that would have a payload of 50 to 200 kilograms, but the project was canceled before they were flown. What if we could use electricity to get to orbit? I did a video on spin launch, a non-gun electric launcher, a while back. The link to the video is in the upper corner. The first approach is known as a railgun. Railguns are much loved in science fiction. This is a weapon from the Halo universe. They are very simple. You take 2 metal rails that are spaced a fixed distance apart. Between the rails, you put a metal part known as an armature that bridges between the 2 rails so that current can flow between them. It's typically made of aluminum for lightness. Hook up a nice DC power source like a car battery, and the resulting magnetic field will cause the armature to be accelerated down the rails. Simple and clean. Assuming the car battery I show here can put out 12 volts at 1000 amps, and the system runs at 25% efficiency, we can do some calculations. If the rails are 6 meters long, and the armature plus payload is 1 kilogram, we can expect the final velocity to be about 38 meters per second, 85 miles per hour, or 137 kilometers per hour. Not really very impressive. At 38 meters per second, the projectile won't travel very far. We can push higher voltages or more current to accelerate faster, but the benefits aren't that great because as you move faster, you spend less time in the gun accelerating. If you push up to 10,000 volts and 100,000 amperes, you can get a speed of about 1,650 meters per second for that 1 kilogram payload. Not really very exciting. An M1A1 tank can fire a 7 kilogram projectile at that same 1,650 meters per second. The U.S. Navy did research to replace existing small guns on destroyers with railguns. This is a research prototype. As you can see, there are huge cables to carry the necessary power. Here are 2 more refined prototypes. In the background of the left picture is the huge capacitor energy storage bank to provide the amount of energy required. This video shows a number of different views of a test firing of one of the prototypes. Here are some still pictures from that test and another test. They certainly look impressive, but there's something troubling going on. We are using electricity to shoot an inert projectile. Where is all the flash and fire coming from? It turns out that if you try to slide a piece of aluminum at 2,500 meters per second down a steel rail, you tend to convert some of the metal into a very fine powder, which burns very brightly in the air. The Navy spent $500 million on research and managed to fire a 25-kilogram projectile at 2,500 meters per second. But the rail wear problem was deemed to be too hard to solve, along with the requirement that the ship needed 25 megawatts of power. This program was canceled in 2021. There have been space launch versions proposed. If you could build a 5-kilometer launcher, provide it with 10 gigawatts of launch power, you could accelerate a 100-kilogram launch mass to 7,211 meters per second. Theoretically, of course. You then need to use the onboard rocket to circularize the orbit, and that means you are down to less than 50 kilograms of payload. There was no discussion of rail wear. The next electric option is a coil gun, also known as a Gauss gun. You take a coil of wire wound around some sort of hollow form, you add a big capacitor or some other way to store a lot of power, and then a switch to connect the capacitor to the coil. You build a series of these, and the inside of the coils becomes your launch tube. Inside the launch tube, you put your projectile, and then you fire the coils in sequence. Each coil provides a little bit of acceleration, and the projectile keeps speeding up as it goes down the tube. If you need more acceleration, you just add more coils. One of the challenging parts of the coil gun is to make sure the coils fire at the right time. To do this, you need an accurate way to determine where the projectile is and how fast it is going. You can do this with a laser rangefinder at the launch end. It will fire a laser pulse that will reflect off the back of the projectile. When the projectile moves farther away, the pulse will take longer to return. Here's a proposed space launcher using a coil gun. You build a 0.8 meter barrel that is 960 meters long inside of a mountain, using 9,000 individual coils. Each coil will have a power supply that can supply 1.7 million amps of power at 56,000 volts. That will give you 6,000 meters per second with an 1,820 kilogram vehicle, and ultimately a payload of 100 kilograms to a 500 kilometer orbit. The projectile is shown in this diagram. Most of the mass goes to the armature and the solid rocket motor that will be used to place the payload in a circular orbit. The heavy rocket motor is placed backwards in front of the payload so that the projectile will remain stable. And all of this is encased in an aeroshell to protect the rocket and payload from the high heat of launch. This proposal is nicely done and quite complete. Their estimate is that the facility cost will be $4.5 billion and yield a cost per kilogram of $1,300, which frankly isn't very exciting. The cost is dominated by the cost of the power supplies, and if that could be reduced, this is clearly a viable approach. I'll note here that the launch cost numbers are highly suspect. There are just too many variables for it to be anything other than a guess. That will be true for all of these approaches. The next approach is to use a gas gun. Specifically, a light gas gun. We start with a conventional gun design. At the back of the barrel we have the propellant, and in front of that we have a piston instead of a projectile. It's typically made of a dense plastic. Then we add a second barrel, or stage, with a small projectile in it, connecting the two with a tapered block. In front of the projectile barrel we put what is known as a burst disc. This is a piece of metal that is scored so it will break when a pressure is exceeded. This allows a high pressure to be developed in the barrel before the gas starts acting on the projectile. And finally, we have the gas. It's called a gas gun because we are using gas compressed by the piston to accelerate the projectile. It turns out that one of the limitations in the speed of guns is the speed of sound of the gases in the barrel, and that depends on the molecular weight of the gas. You want a light gas with a low molecular weight, and that's why it's called a light gas gun. Helium is safer and is used in some research settings, but it's lower performing, much more expensive, and a finite resource, so hydrogen is a better choice. In operation, we fill the space in front of the piston with hydrogen pressurized at a few times atmospheric pressure. We then ignite the propellant, which drives the piston forward quickly and pressurizes the space in front of the piston, but this pressure is still restrained by the burst disc. When the pressure gets high enough, the disc bursts, letting the very high pressure hydrogen in behind the projectile, and it exits the gun at high speed. The first stage creates the high pressure gas, and the second stage launches the projectile, so it's a two-stage light gas gun. Here's what qualifies as a big research gas gun. This gun at Arnold Air Force Base has an 8-inch barrel and can accelerate a 12-kilogram projectile to 4 kilometers per second. Higher velocities are easily achieved, but only with tiny projectiles. Here's a real proposal for a launch system. It has a 25-inch, or 0.65 meter barrel. It uses hydrogen heated to 1500 Kelvin injected into the tube, and it can launch a 680 kilogram projectile at 7 kilometers per second. It uses a multi-injector approach. There is a single base injector at the starting point, and then 15 pairs of injectors along the barrel to add more gas to keep the pressure and therefore the acceleration high. Here's a series of steps. Number 1. -1 hour. Prepare the pressure injectors and pump all of the air out of the launch tube. Number 2. Launch. Number 3. 0.435 seconds. Discard the sabot. Number 4. 300 seconds. Jettison the heat shield and reorient the projectile so the rocket motor is pointed in the correct direction. 5. 545 seconds. Fire the solid rocket motor. 6. 636 seconds. In orbit with 165 kilograms of payload. Then, number 7. Spend 2 hours pumping the hydrogen out of the tube and storing it for reuse. Here's the projectile. Note that it uses the same rocket motor backwards at the front approach. Here are the economics. For an 113 kilogram payload, the facility cost is estimated at $300 million. It's much cheaper than a coil gun because the barrel is simpler and you don't need all of those power supplies. If you launch 300 times per year, it will cost $3,486 per kilogram. Not very exciting in terms of numbers. That's about what a Falcon 9 costs. Green Launch is working to build a light gas gun launch solution. Their Phase 1 solution is targeted at launching a small payload of unspecified mass at 2,000 meters per second and 100 kilometers in altitude. That is pretty similar to what Project HARP did. Phase 2 is to reach 200 kilometers in altitude, launching at 3,000 meters per second. Phase 3 is to launch at 6,000 meters per second to 100 kilometers with a real payload and put a 1-pound CubeSat into a 300 kilometer orbit. I couldn't find any details on what size or length their launch tubes will be, but it's a fair guess that they will require multiple injection stations to get 6 kilometers per second. Their assertion is that a facility that costs $200 million can launch 91 kilogram payloads, and that if they do 7,000 launches per year, the cost will be about $240 per kilogram. For comparison, that's about 40 Falcon 9 Starlink launches, so it's not a totally ridiculous amount to launch, but it is pretty optimistic in terms of business. I do think gas guns are reasonably practical. We finally get to the last approach, the ram accelerator. It's not strictly a gun, at least not like the ones we've talked about, but it does have a projectile and a barrel, so I'm calling it a gun. One of the problems with conventional guns and gas guns is the reduction in pressure as the projectile moves away from its starting point. The ram accelerator is an attempt to fix that limitation. It's similar to a ramjet engine. The diffuser in front of the engine is shaped to take incoming airflow and compress it so it can be mixed with fuel and burned to generate thrust. A ram accelerator uses a projectile that is shaped like a ramjet diffuser. The walls of the launch tube serve the same function as the walls of the ramjet. They help compress the contents of the tube and heat it up. The tube is filled with a flammable mixture of fuel, methane or hydrogen, and oxygen, and that high pressure makes it hot enough so that it burns and generates thrust behind the projectile, pushing it forward. There is effectively a traveling wave of pressure due to the combustion right behind the projectile, consistently pushing it forward. Here's how it works, and I apologize for the paragraph marks on the image. A projectile is first accelerated with a conventional gun, fueled by solid or gas propellant. The ram accelerator is filled with an appropriate gas mixture, and there are diaphragms across the entry and exit to keep the gas confined. The projectile then enters the ram accelerator. Like a ramjet, it needs enough starting velocity for the gas to ignite. It then flies down the accelerator with combustion pushing it from behind. Ramjets are limited to about Mach 6. Ramjets are limited to about Mach 6 because the shock waves in the inlet reduce pressure and thrust. There's a variant of the ramjet known as the scramjet, or supersonic combustion ramjet, which moves the combustion earlier and allows higher speeds. The same approach can be applied to the ram accelerator. At lower speeds, there is combustion behind the projectile, and at higher speeds it moves up to the side of the projectile. Getting this to work will obviously require careful design. The ram accelerator has one significant advantage. A ramjet or scramjet is limited based on the speed of sound in whatever air it is in. That's about 330 meters per second at ground level, but only 275 meters per second at 10,000 meters. The ram accelerator can use fuel mixtures that are tuned to change the speed of sound in different sections of the launch tube. The beginning has a lower speed of sound when the projectile is going slowly, and the later sections have a higher speed of sound. Note how the low speed on the left uses a heavy mix of methane, oxygen, and carbon dioxide to keep the speed of sound low. And the high speed on the right, it is using a mix that has a lot of hydrogen to keep the speed of sound high, and therefore enable faster speed at a given Mach number. One of the problems with the ram accelerator is that the pressure wave quickly dissipates behind the projectile and reduces thrust. Newer designs use baffled tubes. The baffle contains the combusting gases until the projectile passes, and the combustion then propels the projectile from behind. There is, of course, a design for an orbital launch system. I give this one extra points for the 1970s conceptual art. It's a big design. The tube is 1 meter around, and the vehicle is 0.76 meters and 2,000 kilograms. They are targeting a 500-kilometer circular orbit. They present two options. The economy option uses a 3.8-kilometer launch tube that gives 8 kilometers per second of velocity and 375 kilograms of payload. The full meal deal option uses a 6.7-kilometer launch tube that gives 10 kilometers per second and nets 866 kilograms of payload. That all sounds great. But here's a dose of reality. The majority of the research has been done at the University of Washington on a small research setup with a 16-meter tube, trying many different variables including different gas mixtures, different propellant designs, different tube designs, etc. Top speed tested is about 2,300 meters per second, which is a long way from 8,000 meters per second, but it's pretty clear that it actually does work. Here's a picture of a projectile in a clear tube, and you can clearly see the combustion behind it as it flies to the left. Time to evaluate the options. Conventional guns are simple and well understood, but they top out at about 2 kilometers per second. That's just not enough velocity to make it worthwhile, so there's no practical solution here. I'm going to give it a D on practicality. Railguns are simple in design, and the gun part is relatively cheap. Unfortunately, there's no way around the problems of the armature-to-rail contact. The friction is going to wear down the rails over time. You might get away with that with a 16-meter gun barrel. It's just not going to work with a 5,000-meter space launcher. It also has high electrical requirements. It also gets a D. It's great at making big, pretty pictures, but I don't see how you can make something real out of it. Coil guns have a lot going for them. The coils and power supplies can be modular, and that could bring down the price a lot in theory, and they should last well as they are low contact, and they should be able to get high velocities. On the downside, those high-power coil modules are always going to be expensive, and they need a lot of power. I think you can build ones that work, so I give it a C, but the construction costs look to be pretty high, and if you mess up a barrel, it's going to be very hard to fix. Light gas guns have a long research history and are very well understood, and they're pretty simple. They don't require large amounts of electricity. The research versions reach high velocities with tiny projectiles, usually measured in grams. They would need to be scaled up a lot to do orbital launch, probably with multiple injection. I think you can probably build one that works, but it's not going to be simple the way the research ones are. I'll give it a B grade. You can get a decent velocity out of it, and it's not too complicated, except that you need the multiple injection approach to get the speeds you really want. RAM accelerators have generated a lot of research interest. They are simple conceptually. They use a chemical fuel, which is a great way to generate the required energy, and they look like they are tunable with different fuel mixes. The big downside is that nobody has built big and high velocity versions. I'm going to give it a B. It's the most promising approach I've seen, but lack of research is concerning. I talked a lot about spin launch in the other video. It's nice that it only requires small amounts of power over the long spin-up time rather than a bunch really quickly, and they get props for having real hardware. But they haven't been very open about the velocities they really expect, and they are talking about a tiny payload for a fairly big vehicle and a 2-stage rocket. They'll get a C, with a plus added because they have real hardware and it looks like they have decent funding. That's all I have to talk about. If you enjoyed this video, please watch this Punkin' Chunkin' video from 2021.